arms at the elbows, like, yeah. So if you could all like link arms, can I borrow you a minute? Yeah, can you link arms like this? Yeah. So if you can link arms, excellent. So you're now a spacecraft structure. You've seen that, guys, right? Yeah, this looks like a spacecraft structure, doesn't it? So what happens if I heat you all up at the same time? Any ideas? What happens if I heat up a big lump of metal? It's going to expand. So what happens, guys, if the metal expands, exactly, move up. You need to keep holding on to each other, otherwise you're no longer a structure. Excellent. So it's going to expand. How about if I cool it down? It's going to contract, it's going to shrink, get really, really tiny. Excellent, excellent. So my spacecraft structure does that. That's cool, that's nice, especially if we heat it all up at the same time. How about if you guys are getting warmer? So if you guys are getting warmer, yeah, you're going to expand. Oh no, my structure's the wrong shape now. Okay, right, so I'm going to cool you back down to where you were when we built you, so back to linky elbows. How about, do you think you could do as if the sun's coming from a different point? So if the sun comes from behind you first, and then it's moving, yeah. Okay, and now it's going to move right around to here. Are you going to stay as hot there when the sun's moved to here? You're going to move back in again. Right, okay, so as we move around, can you get the idea, basically? The structure's going all over the place. Excellent, thank you very much, volunteers. You can go back to your places. So, thermoelastic distortion. Yeah, round of applause for my volunteers. They did really well there. So, thermoelastic distortion causes all sorts of problems. Anybody here like taking pictures? Photos and things, yeah, a couple of hands up. People like taking pictures. So, if you have a really expensive, shiny, it's not shiny, I've got to stop saying shiny. If you have a really beautiful camera lens and you've spent, I don't know, 10 years designing just how perfect that lens is going to be, and then your crazy thermal engineer over here puts like a big lump of heat on one side and doesn't heat up the other side the same, what happens to your lens? It's not the same shape anymore, is it? And you've kind of ruined the picture you were taking. So that's the whole point. So that's why these things are inside the spacecraft. These like to be cold. They like to be cold all the way across. Actually, Metis, the bottom one there, you remember the mnemonic, please make every sausage spicy, yeah, Metis. So Metis at the bottom there, that likes to be cryogenically cold. It's looking at the sun. So it has a cooler on there that's going to take the heat away. So it's basically, what that cooler does, it might cool down Metis's lens. It cools it down to around minus 120 degrees, but that heat's going somewhere. Where's it going, guys? It's going in the box. It's in the box. So that's what all these things are down the side. So that's us actually controlling the temperature of those different things. So we need to keep those temperatures nice and cold. Yeah, so the other thing that I've got on my spacecraft, turns out spacecraft are hard, aren't they? It's like the ideas are pretty good. We had 3 basic ideas there. There's another problem area on the spacecraft. Crikey. That's these little things here. So when the rocket's launched, not deployed, everything's all folded back up again. That's what this thing here is, by the way. This is a launch vehicle adapter. I had so much fun making this. This is a launch vehicle adapter. That's the bit where it sticks onto the rocket. And it's going to be inside a fairing. I don't really care what happens there because it's at roughly build temperature and it's even got power to the spacecraft up until it launches as well. So everything's all folded up. It gets launched and then eventually it gets kicked out the top of the rocket and we start deploying things here, there and everywhere. But it's not just going to sit in one place in space. It is moving around quite a lot. How do we control how the spacecraft actually moves around once it's actually up in space and it's no longer stuck on a rocket? We have thrusters, yeah. So Solar Orbiter has a lot of thrusters. That's what these little bits of pipe cleaner are. So they're actually all in little pairs. So it has 4 sets of 4, and it's got a little 2 here. So those 4 sets of 4 can do quite a lot, and then it has another 2 because those 2 help it do this, if it ever needs to. So thrusters. So Solar Orbiter works on a chemical propulsion system. It means that we're kicking out essentially little bits of fire. It's got a plume. Hot or cold? Is that plume hot or cold? It's hot. They don't make my job easy, do they? They don't make my job easy for me. So, turns out, thrusters, they get hot. What happens if you make spacecraft fuel too hot? Anybody want to guess? Huh?
Blows up.
It blows up, it explodes, yeah. So we kind of don't want to do that. So we can cope with the temperature on the thruster. So for temperatures on the thrusters, I should know this, I just wrote a report about it. The thrusters themselves will get up to around 90 degrees. The fuel can't really get much above 45 degrees because that's when we're starting to get a problem. But when you're firing the thrusters, it's a bit like convection. And what happens is the fluid comes from the spacecraft through the thruster, and it's actually just taking a lot of the heat away. So the heat's not coming back into the spacecraft. When you've got a problem is, you turn the thruster off, you've no longer got a whole load of fuel taking away the heat, and actually these thrusters, they're hot on the outside of the spacecraft, and the heat's going to conduct right the way back up those pipelines. So we make all of our pipelines out of titanium. If anybody's ever worked with titanium, it's apparently, according to the technicians, it's really, really horrible because it doesn't want to do anything. It's really hard to cut, and when you can cut it, it just makes a mess. We don't really want to put a whole load of dusty bits. So like I had a bit of tree on the front of my heat shield earlier, we can't send stuff like that into space. So if your pipe is made just so, then if it isn't the right length, what we tend to do is we put extra bends in it because it's easier to do that than cut it and to clean it. It's also quicker. So what we want to try and do is avoid the heat soaking back into the rest of the spacecraft. We also need to make sure that when we are firing the thrusters, that wherever those plumes actually face aren't going to interfere with all of our instruments. Yeah, I think that might actually be all the problems of Solar Orbiter from a thermal perspective. Does anybody have any questions? You've got ages, I've got like 15 minutes left. And then you'll probably remind me of something else and I'll waffle on for a bit longer.
What proportion of the satellite is bus compared to the instrument?
Ooh, that's a really good question.
Just roughly 50%, 10% is instrument?
I would say it's going to be at least 30% is instrument. I kind of don't need to know that. That is very much a structural type thing. So I'm actually going to waffle a little bit about how I fit in with the rest of the spacecraft. So I said before, solar array guys, they'd love to have the solar arrays facing the sun all the time because then they get lots of power. Also, the power guys, they're not so keen on us because it turns out when the spacecraft is at 1.5 AU and a long way from the sun, and we've designed it for being in a really hot environment, that we just want to switch a whole load of heaters on because it's cold out there. So we're using a lot of the power that the power guys have actually put on there. The mechanical guys, they make sure that everything doesn't shake to pieces on the way up. And so that's where the whole proportion of the spacecraft would come from because they will know exactly what mass is where. They don't like it when we start adding lots of extra mass in terms of, I don't know, trying to couple something to something else a lot better. But what the mechanical guys do to us, oh, it's so rude. They try and take mass off the spacecraft because it costs a lot to launch stuff to space. So what they do is that they take mass off the spacecraft and it's like, you've taken my conductive path away. You're going to have to put that back in. So this is how engineering works. It's how tying all those different things together. Yeah. And it gone. And it, yeah.
So does the surfaces degrade? So you get in 10 years' time?
Oh, that's a great question. So yeah, all of our spacecraft degrade. It turns out if you put something in a radiative environment, in fact I think one of the other girls is talking about that stuff, there's a giant cow somewhere, it looks awesome, it's like a life-size cow, she's talking about effects of radiation on the body, but if you put something in a radiative environment for long enough, it's going to go black. It's good, we started off black already, but that means our telecom space, in fact all this shiny stuff is not going to be so shiny. The nice white eye boom, it's not going to be so white at the end. So what we do is that we analyse everything for start of life, well, beginning of life and end of life. It basically means that we will put a whole load of the materials in an oven and we just blast it with a whole load of radiation for as long as possible and see what happens and see how those colours change and how they develop. So the HGA, I've got it modelled as white, mainly because I had white felt and white pipe cleaners, but it was a real option for us. And the white paint that we're going to be using on Solar Orbiter, I think on our medium gain antenna, for when the high gain antenna is out of action, just in case. It's called Embio White. And I learned something about this. The materials guys told me this. All white paints are black paints. that doesn't make sense, they're definitely white. No, they're all black paints. All the paints that we use, they're black, and then they have colour added on top. So they're all a black pigment base in the first place, and then we add everything else on top of it. So Solar Orbiter's using something called Embio Black, which is why we're using the Embio White potentially. Embio Black is crushed beetles. The materials guys, they get all sorts of fun. So yeah, so we'll look at something as it is, as it's perfectly built and newly clean, as it comes out of the clean room and it's installed on the rocket, because we need to know how the heat transfer is going to work as soon as it's ejected into space and as it starts on its great big journey. And then we also use different properties if we're particularly sensitive to temperature changes. We would do like interim points, but then we also do the end of life to make sure we know exactly what's going to be going on. So the end of life for Solar Orbiter, nominally, it's a lovely word, isn't it, is 7 years. So that means that we are guaranteeing that the mission will run for at least 7 years, and then it has a further 3-year operational period. That means that if it's still working, we're just going to keep on running it as long as possible. They're expensive, they take a long time to design and build. Solar Orbiter's been on the go for about 8 years now, and it's due to launch in October 2018. Turns out doing things, all that great new science, and lots of new materials, Embio Black, Embio White, a new type of heat shield, takes a long time to develop them all. So we want to get as much science out of that as we can do. And we apply the same thing to all our spacecraft too. Excellent, thanks for the question. Anybody else have any questions?
How long is a solar day? So with the spacecraft run, if it's looking at the same sun,
So
how long does that take?
it's going to rotate at the same speed as the outside of the sun. Actually, I don't know. I know that's what it does, but I have no idea how long that takes. So we see solar maxima and solar minima, so the most energetic points of the sun and the least energetic points of the sun in a roughly 11-year cycle. There's also a larger 22-year cycle. And that does affect my analysis. So there's a lot of spacecraft up there already, and we have a lot of data of how the sun actually performs. I use that in my software analysis. And so what we do is that we use a lot of the trends that we've seen for the sun and its sun's behavior over the however many years we've been measuring stuff, plug that all into our computers, try and predict what it looks like. So initially Solar Orbiter was due to launch in 2016. So we had all of our analysis set up for beginning of life properties of 2016, and it's now October 2018, so we've had to rerun everything again. Because we need to make sure that it's going to work. We can't fix them. Once they're up there, we can't fix them. What we can do once they're up there is that we can use our communications device, we can change the software, but that's it. We can't really do anything else once it's up there. So we need to make sure the hardware works. So we do tend to use some pretty old-fashioned bits of hardware, but it works. It works and it works and it works, and so that's why we don't tend to change things until we really need to. But that's so. An example of when we change things because we really needed to would be Swarm. Has anybody heard of the Swarm missions? Excellent. Sea of blank faces. So Swarm is an incredible mission. It's 3 satellites, and they fly in formation all the time. All the time. They're up there right now, and they're above the Earth's surface, and they're actually measuring the Earth's magnetic field. They're actually in a low Earth orbit, which means that they interact with top edges of the atmosphere, charged particles, moving metallic surfaces, magnetic field, and you're trying to measure a magnetic field. You can't be generating extra magnetic field if you want to measure a magnetic field accurately. So what we did with Swarm is we use carbon fibre. Carbon fibre has been around a long time. A lot of aircraft are built out of carbon fibre now. But for Swarm, it was our first. I think some other people probably have done it before, but it was our first spacecraft made out of carbon fibre because the science required it. And now, 6 or 7 years on, we're now starting to move into our telecommunications satellites being made out of carbon fibre as well. So they do start to drift in, but it takes quite a while. Anything else? Yeah.
Should I stick mirrors on the outside of my fridge?
Your fridge has quite a big wall on there, doesn't it? I guess it depends what they got on the inside. Is it not working very well?
No, I'd utilise your skills in a domestic environment. Would it be worth doing?
Probably not.
Well, what colour was the optimum for a fridge?
I don't know. Convection's really good. You've got convection though, so convection's really good for moving heat around. Once you've got convection in the picture, most problems go away. Yeah, it dominates everything else. It's 40 to 70% of all heat transfer is through convection.
If I take my fridge out to space.
Yeah. I mean, we looked at that. We kind of wanted to put an ice pack on some bits. Some bits are just getting really hot. Any other questions? 5 or 6 minutes left. Oh, I could start.
You were talking about the elliptical orbit.
Yeah.
And you wanted to do that to match something that the sun was doing.
Yeah. So.
What was the sun doing then?
Can I just have anything? so the sun isn't just like there. It has its own rotation speeds as well. So what we're trying to do is we're trying to match the speed that Solar Orbiter orbits the sun on its closest distance at the same rate as what the sun actually, as how the sun rotates. And the point of doing that is that we can actually see how the sun's surface develops. If you've ever seen the pictures of the sun, it's got sunspots on there, and after a while the sunspots start joining together with like a plasma worm, and then and that's actually magnetic field. Oh, I'm trying to remember back to my physics degree. It was a while ago. I'm going to give you that back. So thank you. So what happens is the different layers of the sun are all moving together, and because they're different densities and they're different levels of charged particles, you end up with interacting magnetic fields, and so then you're starting to interact energy, and so you've got two black spots. They join together with a plasma worm. And that's actually where the energy is like escaping out of the sun. And the charged particles that is the sun's surface, they start following the magnetic field that has joined up between the two different black spots. And then that's where a solar flare comes from. As soon as you start building up energy, you'll get a solar flare, coronal mass ejection, they've got all sorts of names. And that's actually pretty dangerous for our spacecraft. For those instruments on the front that are looking through the heat shield, they can't cope with that amount of rubbish. Charged particles on the surface of their lenses, so they have little doors. It'll take us over 20 minutes to communicate with the spacecraft. It doesn't take that long for a coronal mass ejection for us to detect it at Earth, which means that we can't actually do anything about it. If we detected a flare at Earth, it's already been a problem for our spacecraft, and we've actually ruined the instruments. So it has these little doors on the front that can automatically close it. So I did mention earlier that once the spacecraft is up there, pretty much it's doing its own thing and it's looking after itself. If something goes wrong, so radiation, it will permeate through the spacecraft. It might scramble some electronic circuits. We time everything on the circuits. It means that we know how long things should take to move from one part to the next part to the next part. It'd be a little bit like if you had a great big line of people and you've got a message and you want to run it as quick as possible, but you know how fast somebody runs. You know how long your message should take to get to the other end of South Bank. If you know how far each individual person can get there, you know if something's gone wrong, if somebody's tripped to something because they've not made it at the right time, which means that we know then if our electronic circuits aren't working, so then we can resend the software, we can make sure that things are starting to work properly as they are doing. The software guys do some really incredible stuff because they're doing all that on pretty low power as well. It's not, if you have like a commercial microwave, that has pretty much the same sort of power as what our spacecraft has, only they're a lot smaller. And you can fix them a lot easier. Any other questions? No, see your face.
I realise it's not your territory,
yeah?
but you've referred to what was it, the acronym for going around Venus?
A VGAM.
Slingshot effect.
Yeah, it's a slingshot effect, VGAM. It's Venus Gravitational System.
It feels like a free lunch, doesn't it? But can you give a layman's explanation?
I'll give it a go. Right, box, spacecraft, excellent, thank you. Right, so the idea. All right, I have to think about this. If you've got something in space and it's in orbit, the idea is that it's going to rotate with the planet. So geostationary Earth orbit's a really good example of that. That's where we just put it out there. It's level with the equator and it's going to rotate. I'm going to be the Earth. I'm going to do this. It's going to rotate at the same speed as I rotate. That's pretty much how geostationary Earth orbit works, and it's at a nice position that it's always going to stay there. The idea is that actually the spacecraft is always falling to Earth, it's just it keeps missing, is how I like to think of it. If you're a lot closer into Earth, so like the International Space Station, which is, I think, around 400 kilometres, that's going to fall in quite a lot quicker. And it does, because it suffers atmospheric drag up there. So whenever we service the ISS, International Space Station, we give it a bit of a boost and we push it up a bit higher so that it can fall a bit further again. So what we can do as a slingshot method is if we put it in orbit, it doesn't actually take it any power for it just to stay in a circular orbit around that one planet. We just get it into the right orbit. So if we can get it into the orbit around another planet, we now don't need to drive it with fuel as it's doing this bit, because it's moving with the planet itself. It's using the planet's gravitational field to actually essentially save fuel. It's a bit like coasting. It's a lot like coasting. Did that make sense?